So energy density is the amount of energy that comes from a certain volume of fuel. So how many joules per meters cubed? And we need to be able to go from energy density to specific energy, and both of these are really helpful values, and we need to be able to derive, how to get back and forth from these, and they may specifically ask you to do that on the IB exam. Now, energy density is the amount of energy per volume of fuel in meters cubed, and therefore, we can work from here to get to specific energy. Density is mass over volume, so we know that, and we can replace, cross multiply the density times the volume to get mass, and rearrange to get volume. Then we can place that in here, so we end up with Q over mass over density, and then we can multiply the top and bottom by density, and we get energy density is equal to Q over M times the density. Now, amount of energy per mass is specific energy, and so this is how we go back and forth. If we want, specific energy, we just need density, and then and we can get it. And so this is the final relationship: energy density is equal to the specific energy times the density of the substance. So let's apply this here. We have uranium. The density of uranium is 2 times 10 to the 4th kilogram per meters cubed. The energy density is 1.3 times 10 to the 18th joules per meters cubed. How much energy is in 3 kilograms of uranium? And this would be a good chance to practice the derivation from scratch and then solve it out. So go ahead and give this a try, and when you're ready to check, you can hit play to continue. Okay, so we've got the 1 kilogram of uranium. Energy density is Q over V, and we can substitute in. When we do that, we get the amount of energy over mass over density, multiply top and bottom by density, and so we're left with energy density equals specific energy times density. And we have our values here. We have the energy density is 1.3 times 10 to the 18th joules per meters cubed. The density is 2 times 10 to the 4th kilogram per meters cubed, and the mass is 3 kilograms. The specific energy, therefore, is 6.5 times 10 to the 13th joules per kilogram. And for 3 kilograms, then, we'll get a total of 1.95 times 10 to the 14th joules. Now, when we're looking at efficiency, it's important as well here that, again, we're looking at, what we have or what you get out over what you put in. And that's efficiency. And we've already reviewed about solar panels, where it's, heating up the water that's going through the pipes and making it hotter. So let's go ahead and try this here. The intensity of the sun is 900 watts per meter squared. At this particular location, the solar panel is 3 meters squared. Now, this is a 45% efficient solar panel, and we want to look at how much useful power is there, and then if we had 10 kilograms of water, how much would the temperature go up in 15 minutes? And so what value that you're going to need here for this is the specific heat capacity is 4186 joules per kilogram degrees Celsius, and you'll need that for that. But yeah, go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so let's see how we did there. Here's our panel. It's 3 meters squared is the area. The intensity is 950 watts per meter squared, and therefore the power there is 2,850 watts. But again, it's only 45% efficient, so we're only getting 1,282.5 watts of effective power out of that, which now we can use for water. So if there's water passing through, and we have 10 kilograms, and we have 15 minutes, we can figure out the amount of temperature increase, and of course, we need to use specific heat capacity equation, Q equals MC delta T. And we've got the effective power output. Time is 900 seconds. And therefore, the amount of energy we're dealing with is 1,154,250 joules. And the temperature increase, therefore, would be 27.6 degrees Celsius. So specific energy with fuels, here's a couple examples here where we have specific energy, and we've got coal here, we've got wood, we've got gasoline, how many megajoules per kilogram. And again, this is based on burning it, and getting all the energy out of it, how much energy, specific energy there is. So let's try this one here. We have a truck that's 35% efficient, requires 60 kilowatts of output energy to function. If the energy density of gasoline is, really specific energy of gasoline is 47 megajoules per kilogram, how much gas in kilograms will be needed for 30 minutes of travel? So yeah, go ahead and pause the clip and give this a try. When you're ready to check, you can hit play to continue. Okay, so here's our truck, 35% efficient. And remember, what you get out over what you put in. And that's another way of writing this. How much work do you get out of your QH? QH is what you put in, and then W is how much you get out of it. Again, you can use, efficiency is equal to how much you get out over how much you put in. And getting out here is practical work. What you put in is the QH. And so therefore, for 1 second, we're dealing with 60,000 joules per kilowatt. So in 1 second, that's what we're dealing with. And so the amount of energy in 1 second is this much. That's QH, that's what needs to go in. Therefore, for 30 minutes, and then again, this is just for 1 second. So if we need it for a full 30 minutes, we can multiply that by 1800 seconds. So the total amount of energy is 3 times 10 to the 8th joules. Therefore, we can divide by 47 times 10 to the 6 joules per kilogram, and we're going to need 6.565 kilograms of fuel for that 30 minutes of travel.